Hello everyone. My name is Gary Mooney, if I haven't met you already, and I'm from the University of Melbourne. And today I'm going to be talking about one of my projects I've been working on, where we're generating and detecting large-scale entanglement on the IBM Quantum devices. So first, we're currently in the NISQ era, so the noisy intermediate scale quantum era of quantum computing. And these are a whole bunch of quantum computers that are out there at the moment. Last talk, Daniel was mostly talking about analog quantum computing, where we have like a quantum annealer. So these are all the digital quantum computers that I could find. And so we've got the 433 qubit Osprey device by IBM. And then we've got for the superconducting qubits, we've got the Google, we've got the one from China, and the Rigetti. And then we've got the photonic quantum computers, so we've got the Xanadu, the neutral atom. They recently announced that they've got a 1,180 qubits. So that'll be interesting when they release that. And then we've got the trapped ion quantum computers, IonQ, Continuum, and we've got Intel with the quantum dots. They're really small. So the Osprey device, actually, I should have included the photo, but I've got a photo of it, the chip, and it's like this big. Like I can hold it in my hand. That's a fully fledged universal quantum computer. And they run this huge, devices, but most of it's just to cool it down. Like the chip is usually pretty small. Yeah, cool. So with all these devices coming up, we're looking at ways of basically benchmarking them to see how quantum these devices are. Because just having the number of qubits isn't really saying too much, because most of them might not be working very well. And so at the University of Melbourne, we've established an IBM Quantum Hub there. And so we get access to the IBM devices. And so, this talk's going to be mostly focused on those ones. Okay, so I'm going to start off by going through the different forms of multi-partite entanglement that we could be looking at. And as a way to benchmark these devices, we're going to be detecting this entanglement. And so we've got the bipartite entanglement. We're going to be preparing graph states. And then we've got a stronger form of genuine-multipartite entanglement, where we'll be detecting that in GHZ states. And we'll also be looking at teleporting bell pairs. So I'll go into more detail. So we'll start off with entanglement. So just so we're on the same page, I'll just go through some definitions. So just looking at like a pure state. First of all, this thing here is an entanglement graph. So these are 2 qubits. And if we draw a line, then that means that the 2 qubits are entangled. And so this is an example. You've got a bell state. And each one of these are qubits. And there's 2 levels for the state, so 0 and 1. Okay, and it's going to be entangled if it's not separable. For the multi-qubit case, we're going to be looking at, so here we've got 3 qubits and we've got entanglement between each of them. And because it's a pure state, this whole state is entangled. And in this case, we're going to be saying that it contains entanglement, but it doesn't necessarily mean that the state is entangled, right? And we're going to be looking at bipartite entanglement. So this is important because usually when people think about bipartite entanglement, they just think about 2 partitions and then whether you can separate them or not. But we're going to be looking at whether whether you can find a bipartition where you can separate it. So it looks more like that. But in a real quantum device, you've got noise, and so we can't really use pure states anymore. And so we're going to be looking using density matrices. And density matrices can be written as a linear combination or a probabilistic mixture of pure states like this. And so if we can list out these pure states like this, we can define separable as being that we can find a partition, bipartition, where we can separate all of them along that bipartition. So we'll define bipartite entangled as being there's no, it's not separable essentially. And this means that if we look at these pure states, there's these overlapping regions of entanglement among them. And so, yeah, the whole state is entangled, you can't separate it, but it doesn't necessarily imply a stronger form of entanglement, which is genuine multipartite entanglement, where you have a pure state in the mixture that's fully entangled across the whole device. And we're going to be looking at both of these today. If we detect, just to clarify, if we detect bipartite entanglement, that does not necessarily imply genuine multipartite entanglement, but it does the other way around. Cool. So yeah, so in order to, yeah. We use the fidelity. Yeah, so, yep. So if we can show that the fidelity is larger than 0.5, it implies that it's genuine multipartite entangled. Yeah. Yeah, so for bipartite entanglement, we're going to be using a graph state, so a pair of graph state. And it's essentially, it's like a cluster state, but the reason why we're going to be using it is that, first of all, it's going to be robust to noise, because if we measure one of the qubits and we know that measurement value, it doesn't disentangle the rest of the state. It can be generated with which graph? Oh, I'll get into that.
Because I guess this robust to noise depends on the graph, right? I mean, the graph state on a line, I measure a qubit in the middle, I will have to cover the left and right half.
Yeah. So yeah, so I'm just sort of going through the basics first. So yeah, it can be generated with a low depth circuit, and as you'll see, it's also convenient for bipartite entanglement. So this is the definition. It can be generated. So first of all, you choose a graph, and you just define it on that by. So each of these are qubits. In this case, this is not an entanglement graph, so this does not mean it's entangled. This is just the line of the graph state. And you have all the qubits, and you basically do a control Z gate between each of the pairs where you see a line here. And so if you do the circuit, it looks like this one.
But again, for this graph, the n/2 is not correct. I mean, I do a single Z measurement anywhere, I will disentangle it.
Not if you know the measurement.
If I do a Z measurement, I will cut the graph into two parts, right? That's the point of graph states. I can erase vertices by Z measurements.
Oh, so that's not what I meant. So I meant disentangling the rest of the graph.
Oh, everything.
Yeah. Because if you have a GHZ state, if you measure something, even if you know the result, the whole thing is disentangled, like all of the parts. Yeah.
Exactly. Okay, I see.
Yeah, and another cool thing about the graph states is they're quite useful if you're looking at one-way quantum computing. You prepare them often with fault-tolerant correction, like in surface codes or 3D topological cluster states. And yeah. So yeah, how do we now detect the entanglement? So a naive method, I guess, would be to just do full quantum state tomography on the whole state. Yeah, and basically that means that you take all the different basis measurements in the X, Y, Z, I for each of the qubits, and you do all of the basis measurements, and you construct a density matrix from that. However, as you can see, it scales pretty poorly. It's it's 3 to the n number of qubits. And so for 6 qubits, you've got 729 circuits. Go up to 10, you've got this much, and then you've got 20 qubits, you've all of a sudden on 3.5 billion circuits. And as just like a point of comparison, depending on which device you're using, around about this many circuits will be a whole day of computation. Yeah, so doing the whole quantum state tomography is a bit overkill because you're just getting all the information from the state, and we only want to detect a certain property. And so we're going to be using a detection strategy for that. So here we've got our hardware layout, and we're going to be embedding a path to then get our graph state. And actually, I should say, what we're going to do is once we embed the path, we measure the entanglement between each of the pairs. And if it's entangled, we add an edge to the entanglement graph. And as an example here, you've got this 5-qubit device. Imagine it's that we've only detected entanglement between these pairs, and so we can draw this line here. But because there's no entanglement between here, we can separate it, and then that just implies that it's not entangled because it's separable. And so if we can show that it is connected after generating our entanglement graph, then that implies that the device is entangled. Cool, so now how do we then detect the entanglement between the 2 qubits? So first we're going to be using quantum state tomography, but only on the pair of qubits that we care about, plus the nearest neighbor qubits. Then we're going to be using this cool property of the graph state, which is that if we measure these outside qubits here, the remaining state falls into one of these 4 Bell states. And so what we can do is for each of those Bell states, we can calculate the amount of entanglement. And the way we do that is to calculate the negativity of the partial transpose. Essentially what we do is take the partial transpose of these 2 qubits and then calculate negativity as the sum of the negative eigenvalues, or the magnitude of the negative eigenvalues. And it turned out that for 2 qubits, a non-zero negativity is a necessary and sufficient condition for entanglement between them. So we're going to measure the entanglement or the negativity between for all of the projections of. Actually, I did miss a step. So once we do the tomography on these qubits, we mathematically project them out afterwards. So we've got this 5-qubit density matrix. We project them out, and then the remaining we calculate negativity on that. Yeah, and then among those projections, we take the highest amount of entanglement that we found as the amount, like the extent of entanglement between those 2 qubits. Cool, so let's apply this strategy. So here we've got the 20-qubit IBM Q Poughkeepsie device with this architecture. Here are some stats here. We've got decoherence times. We've got T1 relaxation, which is essentially the amount of time that it would take for a 1 to decay down to a 0. And then you've got the dephasing, which is essentially how long it would take for the phase information to be lost. We're going to embed our graph state. And these are the negativities that we've calculated. And yeah, and so 0.5 is maximally entangled. You can't get higher. And then anything, if the error bar goes over this 0, then we don't, that's not entangled for us. And then we can generate our entanglement graph. It's fully connected, and so we can say the whole device is entangled. So at the time, this was the largest state on a universal quantum computer. that we know of that was has been shown to be entangled. And before that, it was this one here, 16 qubits. So yeah, we want to basically scale this to now some larger devices. First of all, we're going to be changing the way we embed our graph state. So instead of just embedding a line, we're thinking we'll embed a graph that matches the hardware layout. So we've got, this is the full hardware layout, but it's also the graph state that we're going to be using. And this is cool because you've got these cycles here. And so if you measure one that's not, then you can still be entangled. And it's still constant depth. And the depth of the circuit depends on the degree of the qubits, so the number of qubits that each qubit connects to, the maximum. And you can sort of use this embedding just to count that. Another thing we're going to be doing is using readout error mitigation. So you've prepared your state in your quantum computer, and you read out all the qubits. And during that readout process, you've got errors creeping in. So essentially, we want to undo those errors because that's scrambling our data for what the state was like before we did the readout. Essentially, the way we do that is we calibrate it. So we have our noisy state, and then we have this calibration matrix, or this basic calibration matrix that we can then multiply to what the perfect state should be in order to get our noisy. And if we can figure that out, we can just apply the inverse to then undo the noise. We're going to be making an assumption here where the amount of correlated errors in the measurement itself is low. And there's been studies, including our study, that was showing that this is a good assumption. It's a very low amount of error. Also, we're assuming that the errors are not quantum, which is also like the amount of quantum in the error itself is very low as well. When I say quantum, I mean like the amount of entanglement it can generate. And another assumption is that the error that we're correcting is all the measurement error, because it can be easily confused with a preparation error. It can be hard to identify the difference. And so, and that's also usually the preparation error is like 2 orders of magnitude less than the readout error. So, so now we're assuming that each qubit has its own independent error. It's not correlated. So now this calibration matrix can be measured in only 2 measurements. So the all 0 and the all 1, and then you just calculate the probability of it going into 0 or 1 for each, and you get this matrix. Cool, and you end up with this. So now to apply this, it can be a bit tricky because so when you have your quantum computer, you might have like 100 qubits or whatever, how many you have. And you end up with like a probability vector or like a dictionary of shots where you have the counts of each of the shots for each of the states that you got. Now, the number of non-zero elements is only going to be as high as the number of shots that you've got. And so if you're using something like 4,000 shots, you're only going to have that many elements. And so that's quite easy to work with. But once we start applying this matrix, we're going to end up with heaps of like non-zero values, and it's going to grow exponentially. So now we've got all of a sudden 2 to the 100 non-zero elements that we have to deal with. And so there's 2 methods that we use here. The first was a method we developed where we apply these single qubit corrections individually, and then the probabilities that have a low the states that have a low probability in the probability vector, like a really low value, we just zero it. And then we apply the next qubit. And so it's kind of like a way to sort of like cut out all of the ones that we know aren't going to be useful to keep in our calculations. And that significantly increases our the speed of correction. And another package that we're going to be using is M3 in the later experiments that we do, which uses some molecular techniques to correct. And another thing we have to keep in mind is because we're using finite number of shots and we're applying this calibration, which could be different to the actual experiment because they're done at slightly different times, and you've always got shot errors, you can actually end up with non-physical probability vectors after correction. So you could get negative probabilities. And so we use an algorithm by Smolin to find the closest, the closest physical probability vector. Right, so all that together, we've applied it onto the 53-qubit and the 65-qubit devices here. Here's some more data here. The Rochester, the errors here are quite bad compared to their other devices. And it's interesting to see that reflected in the negativities as well. So now from this data, we can now generate the negativity, the entanglement graphs. And this is what we get. So here you can see that without the readout error mitigation, we've got you can see these areas of entanglement, but there's a whole bunch of separable pairs as well. And then when we apply the QREM, there are a couple of separable pairs, but the graph is still connected, and so we can say that it was still, the whole device was bipartite entangled. And this device was a lot better, and it's clearly bipartite entangled.
Does this depend on the order in which you did your circuit, or I mean, certain links are not
the order.
Well, I mean, there's some choice in right. I mean, you have 3 layers in which you do your control Z gates.
Yeah.
You can do this in different orders. Will this affect
probably,
why you have separability? Because I don't know which are more stable, the early or the late ones. But,
yeah, it's a good question. I think the late ones are generally more stable, but it's hard to say. And the reason why I say that is because when you apply a controlled Z gate, it can sometimes cause these 2-qubit phase errors to appear that drift over time. That's at least what we've observed so far, but they're still pretty preliminary. But I don't think it'll be too significant, the ordering, because they're quite short in between. Yeah. Cool. But now we're going to be scaling up to even larger devices now. So before we do that, let's have a look at what are the current resource requirements that we have for our algorithms. So doing quantum state tomography on 5 qubits, it's going to take 243 circuits. And if we're using something like 4,000 shots for each of those circuits, then we're looking at like 1 million shots. Okay, so we've got 58 pairs of qubits in the Rochester device, and so you multiply those through, and now you've got 11,000 circuits and 44 million shots.
Why not use witnesses? You should reduce the number of circuits you have to measure quite a lot. No?
So witnesses are a bit, they don't always detect the entanglement.
But you know which state to expect, right? So unless something crazy is going on.
Yeah,
the witness would have to depend on the measurement outcome of the surrounding qubits, which might be a bit annoying. I agree with that.
No, it does. So we're not just detecting how close it is to a graph state, we're detecting how much entanglement there is. So
sure,
even if you know the state.
But you know that you have a specific Bell state, right? So it's easy to have a witness for a Bell state.
Oh, you don't.
Pretty sure it will need less measurements than the full tomography. That's one of the points of witnesses, right? It's much cheaper.
Yeah. But we prefer to use like a more complete calculation. Yeah.
What's the reason?
So the negativity is it's an entanglement monotone, so it's not a witness. It is a witness, but it's not only a witness. It's a.
No, I agree. But if you want to save measurements, it might still be.
Yeah, I mean that could be.
Instead, just measure a witness.
You could do that if you wanted to. Yeah. That's an option. But looking at the resource costs for the 65 qubit, you've got 14,000 circuits. And so when I was running these, it would take, because of the queues and like this was a while ago, so it takes a bit of, like the devices are faster now, but this would take like a whole day to get one full like measurement for the whole device. And the devices calibrate. Yeah, so.
I'm a bit confused. We have the circuits are 3 to the power of n, and n is the number of qubits.
Yeah, that's for the state tomography though, and because we're only doing it for each of the pairs plus their neighbors, we're only going up to 5 qubits.
I see. So that doesn't change, because I was about to ask how you get to 3 to the power of 58 to 11,000 circuits, and like. But okay, if it's only always for 5 qubits, or how does it work?
It's mostly 5, but you do have these, for example, which only have 4.
Okay.
Yeah.
You measure the thing with a dashed box.
Yes. Yeah, I see. Okay.
Yeah, so 3 to the n for state tomography is sort of like an absolute minimal set.
Yeah.
Have you done an overcomplete set to see if you get, better results, or?
To get the density matrix. Yeah. So 3 to the n is the full. So you can do some. Yeah. So normally it's 4 to the n, but you can calculate the I basis measurements from the rest of them, and so you only ever need to do x, y, and z.
But in practice, you would often do an overcomplete set of measurements to get a better estimate of.
Oh, I see.
Density matrix elements.
Well, initially we were.
So I'm just curious if you tried that. Yeah.
Initially we were doing that, but we didn't really find any significant difference. Yeah. So that's why we just used the more optimized version. Yeah. So the devices are calibrated like once a day, or they used to be. And so it was really a struggle to get all the measurements we needed within one calibration cycle.
And you really should use witnesses if you're having trouble doing all the measurements, no? I'm surprised why you refused to.
Well, what witness would you use though? Like. Okay,
I'm not a witness guru, right? But we can talk later. But I mean, it's a witness for a Bell state. I mean, that's standard on witnesses. No, it's not an exotic quantum state you're looking for here.
Yeah, I don't know. The witnesses I've seen depend on the Bell state, but
sure, but
it might not be exactly a Bell state. So the negativity is a better. Like it's a more complete version because it'll.
Okay, I mean, you're just saying you're struggling to get your measurements done, right? Then if it's about certifying it's entangled, maybe you get slightly less good results number-wise, but it runs much faster. So at least you can faithfully say your device didn't drift away, right? So. Well, actually, I agree it's a trade-off, but you just told us you're at the limit of what you can do. Yeah, no, you're right. But we were able to get our measurements within a calibration cycle, and we also did trace the amount of drift as well. So we between a bunch of so we kind of like partitioned a whole bunch of our circuits, and in between at fixed intervals we would check the drift. So we would measure and see if we were getting any and it was okay. It was okay. Yeah. So yeah, you're right. There are better ways to do it, but we were able to get it, and it is a more complete version. So it does. Okay, so IBM released even bigger devices, so we're going to go higher. Here's the IBM Washington device, 127 qubits. To do the method that we were using, we've got 28,000 circuits, which, so I didn't say before, but before we only did one measurement. And so how would you calculate error bars with that? So we use what's the technique called? I can't remember the technique. Where basically we
we resample the measurements statistically, and we can then calculate error bars through that. Can't quite remember the technique. Bootstrapping, yeah. Oh, yeah. But that was actually extremely computationally intensive. And so we prefer not to do that. And so you would need 8 times that to then get some statistics. So yeah, how can we reduce this? So we're going to be introducing 2 optimization techniques here. So the first one is, so I was saying before that we did tomography on all 5 qubits. But if we know what the Bell state should be based on these measurements, then what we can do is basically bucket the measurements into different categories. And that means that we don't need to do tomography on all 5 qubits anymore. We only need these 2 qubits. But we end up with 4 different sets of results. And yeah, we can just calculate the tomography on those. And so it reduces it down to only 9 circuits per pair instead of up to 243. Yeah, and that reduces it down by a factor of 22. And the other optimization is that, so before we were doing each of the pairs as separate measurements, as separate experiments, but we can just do those all in parallel. And so, yeah, you can sort of distribute them, kind of like this, and you can get these, yeah. And we've got an algorithm that does it on arbitrary architectures. But for the IBM heavy hex devices, you can actually get up to 4 rounds, so you can do it quite efficiently. That's with sharing neighbors as well, so allowing that to happen. Yeah, and so by doing that as well, we've now brought the Washington device experiments only down to 36 circuits. And this is a constant number. It doesn't depend on the size of the graph anymore because it's done in parallel. So here are the results. Yeah, you can see that we've got, again, full bipartite entanglement. And we've done it on the even larger device now, on the 43-qubit device. And because of the constant number, we can still do the experiment fine. And keep in mind that these missing edges here are because these qubits are inactive. And we found that if you just count the active qubits, the whole device is bipartite entangled. But otherwise, yeah, we just got 414 qubits. Cool. All right, so we're using this to sort of benchmark the devices. So it would be nice to sort of understand a bit more about what the negativity means. And so we looked at correlating that with the actual errors of the device that we've already got available to us. And so what we're doing is we're taking the negativity between the pair, and we're taking just the gate errors, the 2-qubit gate errors. And we're averaging those gate errors, and we're plotting them like this. So gate errors here, negativity. And you can see that there's a bit of a correlation, but it's not quite perfectly correlated. And we also ran this on all of IBM's devices. So we've got all of these here, and we found that all of them were actually fully bipartite entangleable. And if we now look at the average device C0 error on the X, and then the average negativity, you can see as well that we've got this correlation going, but it's still not exact. Cool, so that's it for the graph state bipartite entanglement stuff. Yeah, so now we're going to be looking at the genuine multipartite entanglement. Yeah. Right, so here we're going to be using GHZ states, and they're essentially a generalization of a Bell state. So we've got 0, 0 plus 1, 1, and here we've got n of them. They're convenient because the density matrix is very sparse, and we've only got non-zero elements on the diagonal corners, all of the corners. And if you look at the density matrices between the GHZ and the graph, we've got, And so that allows us to focus on those elements only to then know what the density matrix looks like to be able to calculate the fidelity. Another thing is that it's sensitive to noise. Like I was saying before, if you measure one of the qubits, the whole thing disentangles. I don't know if that's a good thing or a bad thing. It's good because I guess it's a better measure for how good the device is. All right, and this is how you prepare it. So we start off with a Hadamard gate on one of the qubits, and that essentially turns it from a 0 state to a equal superposition of 0 and 1. Then we apply these C0 gates, controlled on the original qubit and targeted on the next qubit, and that creates a bell pair. And now, if you do the same thing with another C0, controlled on one of the qubits in the bell pair, then it essentially grows out this C0, like this. And in terms of the circuit depth, if you didn't care about the hardware constraints of like which qubits are connected to which ones, you've got this log2 n scaling. But on the IBM devices, you've got it scales like this, square root of 2n. Cool, so then how do we detect it? So like I was saying before, we want to measure the fidelity of the state. And then if we can show that it's larger than 0.5, then that implies genuine multipartite entanglement. It's an entanglement witness for that. And we can categorize these diagonal terms as being the population and the coherence. And we can express the fidelity as being the population plus the coherence divided by 2. So the population is quite easy to measure. It's just the occupancies of the all 0 and the all 1 states. But the coherence is a lot more complicated, and we're going to be using a technique called multiple quantum coherences. So this is what it looks like, the circuit for multiple quantum coherences. We're going to first prepare our GHZ state. Ignore this for a moment. And then we're going to rotate each of the qubits about the Z basis by an angle phi. And that should give us a state that looks like this. So we've got a GHZ, and then we've got this accumulated phase on the extra state. And then if we undo the GHZ state now, we've got, we can then look at how well it went back to the original state, called the overlap signal. So it's just the occupancy of the all 0 state. And if you plot this in these plots here with different phis, then it turns out that the amplitude of these oscillations can be used to then calculate the coherence value that we want. This pi pulse here, essentially, so in the device, you've got these free rotations about the Z basis, and the pi pulse essentially reverses those rotations. And so it's a way to kind of cancel out those errors that might accumulate. Okay, so here's the device we're going to be looking at, and this is the preparation circuit for it. And we're also going to be tacking on an extra experiment where we're also going to be using this parity verification method to error correct it a little bit. So the way it works is we've got these green qubits are not being used in this particular one, and we're using C0s from the neighboring qubits onto that. And if it's a GHZ state, we should always get a 0 state for those 2 qubits. And so if we don't get 2 0 states, we throw out the result. We know that we don't have a GHZ state. And and these are the results. So the top here is where we've got the readout error mitigation applied. And then the red, we've got parity using these parity verification method. And then here's just the standard method. And you can go all the way up to 27 qubits. And this is just the delta of what the parity checkers made to the fidelities. And so you can see that it has improved, but only by a little bit. And because the fidelity is larger than 0.5 within error, that implies that the full state is genuine multipartite entangled. And the whole device is as well. So we want to scale this to larger devices. And what we're going to do is, instead of just, because we're going to run this on this very large quantum device, instead of just using an embedding that we've sort of come up with, we're going to be using a search algorithm. And what it does is there's two parts to it. First, you just choose a qubit, and then you do this breadth first search out in order to, until you get to the size of the GHZ state you want. And then once it gets there, it should be the least depth circuit, because it's gone as much parallel as it could have possibly have gone to get there. And we do this on all the qubits individually, and then we're also we're also preferring the gates that give us the least amount of error based on the calibration results that we have. And we do it for all the qubits, and then we just choose the best embedding out of that. And here's an example of the different depths that you could have. So in this middle qubit here, you can see that it's clearly a lot better embedding. Cool. So by doing that, we've been able to scale it up to 32 qubits. So here we've got genuine multipartite entanglement for 32. And here's just some extra data, if you're interested, of the individual population and coherence values as well. So this is the history of states that have been entangled so far for quantum computing, in particular universal quantum computers. And you can see that, so these are our works that we've got. And then actually this year, not long ago, China came out with this paper where they found a 51 qubit genuine multipartite entangled state, which is quite impressive. They are using a graph state instead of a GHZ state, so it's more robust. But usually graph states are a lot harder to detect genuine multipartite entanglement on. But they're using a different method as well, called randomizer stabilizer measurements, which seems to be quite promising. And their measurements are quite, they require a lot of measurements as well. I think it's like 10 to the 8 shots, so 100 million shots to get those results. So next we'll just look at, so you have this GHZ state, and now we want to preserve the entanglement within it. So the way we can do that is, we after preparing it, we just wait, and then we measure the fidelity at a later time, and then we can plot this. And so for the population, it's just this delay here, and for the coherence, you've got this delay before these unitaries here. And then you can use a method called dynamical decoupling, and we're using two methods here. So this is a spin echo, which is essentially what we were doing already, but now we've got these delays before and after. And then you've got periodical dynamical decoupling, which is where we apply like a series of these corrections. And so we'll have a look at how that works in this device. So the graphs are a little bit messy. I didn't have time to clean them up, but you can see that the ones that stop early, this is just a free decay, so it doesn't have any kind of dynamical decoupling. The blue is where we've used quantum error, readout error mitigation, so those are the ones we're looking at. And so we've got spin echo, this is the population, and then we've got periodical dynamical decoupling here. And you can see that for population, spin echo improves, but actually for periodical dynamical decoupling, it makes the population worse. And that's because every time you apply these gates, they're introducing their own errors as well into the system. But for the coherence, it's a different story. So we've got periodical dynamical decoupling is giving the best results, and then spin echo is still good results, but not quite as good. And then you've got this free decay, which decoheres in 5 milliseconds. Microseconds, sorry. Yeah, and for a point of reference, on the devices we used, the C0 gate error time is about 400 nanoseconds. Yeah, and then here's the fidelity. So yeah, you can see that it clearly helps by quite a bit compared to this free decay. And they're both, even though they're good at different things, they kind of average out to be similar.
10 minutes.
10 minutes?
Quick question.
Yeah.
So the periodic, is this like CPMG? Carper-Cell-Meyer?
Not sure what that is.
Are you basically, are you just doing it forever, or is there a particular length of sequence that's being used for the periodic?
Oh, that's a good question, actually. Let me see this. Yeah, I'm not sure what the DT. Yeah, no, that's a good question. I'm not really sure. Yeah. Yeah. Yeah, those calculations were done by Fidel in our group. Yeah, I'm not exactly sure what he chose for that. Where are we up to? So now we'll look at a phenomenon called super decoherence. And essentially, this is where you have a quantum device, and when you create a state between all the qubits, instead of the individual qubits having a decoherence time that depends only on itself, it actually depends on how many qubits are in the state as well. It's obviously bad for quantum computing because it means when you scale up, you've all of a sudden got everything decohering really quickly. So previously, there was a study done for an ion trap system that showed super decoherence in their device, which means that the GZ decoherence time scales as n squared. And yeah, this is how it is calculated, by the way. We just fit the data where we do it over time, and alpha is the decoherence rate. But just keep in mind that this was just one ion trap system. It doesn't mean they're all like that. This was just this experiment. Yeah, and then there was one done on the IBM device as well that showed no super decoherence for an 8-qubit device. That was a few years ago now. And so now we're going to be doing tests on the more recent device and a large device as well. And so this is what we get. We've got these plots here, these decay curves that depend on the number of qubits. Yep, and if you now calculate that decoherence time and then plot that based on the number of qubits, you can see that this previous result that was done is this orange curve here. And this is our new one. So it's still linear, which means there's still no super decoherence, which is great. And you can also see that it scales a lot better as well. Just keep in mind that we have used dynamical decoupling here, so that could be contributing by quite a lot. But I imagine it would be true because they're using this the 16-qubit Melbourne device, and from memory, it had some not very good stats on it with the errors of the gates and everything. Okay, so the last thing I wanted to go through is the Bell state teleportation. Yeah.
So for the super decoherence, shouldn't that just always occur? It's just that you're not at large enough sizes to see the n squared scaling, or like why? Like what would prevent a GHZ state from showing this, and it still has a Fisher information going as n squared?
I mean, as far as I don't know a lot about it, but as far as I know, it depends on you can model it as being what the qubits are coupled to. So if the qubits are coupled to a single reservoir, then you get this super good decoherence going on. But if they can be modeled as being separate reservoirs in the environment, then you won't get the decoherence, the super decoherence. Yeah. So I don't know if it's guaranteed, but maybe if you things are not perfect in the real world. But yeah, we have no evidence of it at the moment. So, yeah. Yeah, we can just do it through empirical. Yeah, that's right. Yeah.
Before you go to the Bell state, did you consider what is called topological entropy as a measure of multipartite entanglement? I mean, I know that there are other classes of tripartite states which are highly entangled but not GAZ, right? So there are theoretical results which show that the GAZ is very bad in that measure, but other ones are very good. Multipartite entanglement a la Kitaev-Preskill is probably something one should look for, right? I mean, that's they created this topological entropy expression.
Yeah. Which one? Sorry. What's it called?
Tripartite mutual information or topological entropy, and that's a measure for really multipartite entanglement.
Okay, I'm not actually aware of that one. I'd have to look it up. Yeah. I don't know how it relates to genuine multipartite entanglement. Like whether
it is definitely in an entanglement which you cannot discover it by looking at the separation of two blocks, right? So it's really a property of three parties altogether.
Yeah, but what happens then when you have like 100 qubits?
Well, you just block them in a certain way, and you would see the same phenomena everywhere.
Okay. All right. I'm not too sure.
I mean, it's just another very highly entangled state, which is not GAZ, right?
Yeah. Okay. Yeah. Okay. All right. All right. So what we're going to do here is we prepare a Bell state between two qubits, and what we can do is if we apply a CZ gate on a equal superposition state, and we measure this qubit, and we know the measurement, then we can apply this correction to this state here, and it's now essentially teleported the state. And this is similar to what I was saying before, like you have a graph state and you can measure it, and if you know the measurement, then you can, right? And so we do this multiple times, and we can basically hop this beta state across qubits like this. And that's what the correction looks like. Yep. And so we're going to be looking at three different approaches. One is just swapping. So we have this state, and we use a swap gate, which essentially swaps the states of the two qubits using 3 CNOT gates. And you just swap it to the end. We're using this dynamical circuit, which I'll tell you in a second, and then the post-selection, which I'll tell you in a second. So this is the swap gate circuit. We've got this Bell pair being generated, and then we use this sequence of swap gates. So those are our two states, and then we can measure. And these are just basis measurements. We do tomography, and then we calculate negativity, because it's just two qubits, so it's entanglement monotone. Cool. The dynamical circuit, so this is using the teleportation. So we generate this Bell state. We actually have a graph state here because we're playing these CZs on a H. And if we measure in the X basis, which is equivalent to applying another Hadamard gate and then measure in the Z basis, we can then use that data to then correct our next qubit. And the way, so IBM have these dynamical circuits where essentially they can actually do mid-circuit measurements and then use that in the middle of the circuit, the computation, to then apply an actual gate to the system. And that's what's happening here. So we're doing mid-circuit measurements, and then we're applying these corrections while the circuit's running. And we can push all the corrections back to the very last qubit. And this circuit scales linearly with the number of qubits because you have to measure, and we can't actually do the measurements in parallel and correct them all at the moment. Cool, and then we're going to be using this teleportation, but now with post-selection. So we do the same thing in principle, but instead of doing it using mid-circuit measurements, we just measure everything at the end. And then because of what I was saying before, with the you're only going to get one of 4 Bell states, we can then just bucket the results. And this is cool because it means that if we know what Bell state we want for our experiment, we can just keep going until we know we got the right one. And because there's only 4, yeah?
For the slide before, wouldn't it be smarter to classically process all the results and only do a single rotation? I mean, there's right. I mean, you can do classical post-processing of all these measurement outcomes, and you have to do 1x and or 1z rotation.
That's true, but
it compresses significantly.
So you mean post-processing?
No. This the C naught H. Well, the classically controlled not H, classically controlled not H, and so on.
Yeah.
Right. I mean, if you merge this consists of 1x, 1z, or a y rotation, or nothing. Right. That's the 4 things which can happen.
Yeah, that's right.
You can easily classically compute from all those measurement outcomes you had in between.
That's right, yeah.
It's probably much more efficient to do that classically than to run a fairly long quantum circuit in case you want to do this over more than 2 sites.
So that's true, but there's a current restriction with the IBM devices where we can only actually measure one of them at a time, like with the dynamical circuit, like mid-circuit.
But still, I would think it should be faster to... I mean, the control is classical anyway, right? I mean, you have to measure all these things.
Oh, you just mean like combine all of these into one gate?
Exactly.
Oh,
compress
okay,
it to one
yeah.
and figure that out classically what you have to do. Right?
That's true. That's true. But this is not really the bottleneck. This is so this is just X gates and H gates. They're both very cheap on a quantum computer. So you're right. You could get a more efficient, but overall it's going to be way dominated by this. So every time you do a mid-circuit measurement, it causes a lot of because you can't error correct that readout. But it's not statistical. It's like you've got the result. Yeah. 2 minutes? Okay, thanks. So this is the other version. So you've got the Bell pair, the graph state, and so here what we're doing is we're just going to measure all of them. And then, I already talked about this, sorry. We've got the Bell pairs and you bucket them, and then this is cool because it means that if you know what Bell state you want, then you just keep going until you get the right measurements, and there's only 4 combinations, so it won't take you long. So the worst case is you're going to have like an overhead of like 4, which is I think is pretty manageable for this. So let's look at the comparison here. So this is the amount of negativity. And this is the number of hops, so how many qubits we've actually teleported through or moved the state. And you can see the post-selection works way better. But interestingly, the swap method is still better than the dynamical circuit method, and that's probably because we're not currently doing the measurements in parallel, and because we can't really correct those, and they've got a lot of error in them. Also keep in mind that we're using this device, the way we did this embedding is just random. We haven't yet gone through and optimized, the best embedding or anything like that. And we haven't just kept going until we're always above 0. So this could actually, if we're smart about it and we choose a good device, this could be quite long. We could be able to teleport by quite a long way.
If the measurements are the bottleneck, how come post-selected is so good?
Well, the measurements here are done in parallel, all at the same time.
Including the readout measurement. I see.
But also, we can do error correction on this, readout error correction, because it's still statistical, because we're doing it right at the end of the circuit. So we're not doing any conditional logic that depends on the exact state. So it's still a stochastic measurement. We can still run it many times. That's actually a big benefit. We can apply readout error mitigation. So this could probably be a lot better. So it'll be really interesting to see if we can extend this by quite a bit. So to just summarize, we talked about the different forms of multipartite entanglement. We generated bipartite entanglement on up to 414 qubits, and we've used a protocol that is a constant circuit count of 36. And we looked at genuine-multipartite entanglement and the decoherence times. And we did this Bell state teleportation. So this is our team, students, and Lloyd, he's our group leader. So thank you.